And thank you so much for having me. I'm Pedro Mendes. I'm a researcher at Ghent University, and for the last couple of years, I've been working in the usage of catalytic data on the basis of tailored approaches. Yeah, as Dr. Brian also pointed out, it's very hard to get formats or generic tools, format standards for data in catalysis. So I wanted to start exactly by categorizing a bit the different types of data. So according to GCAT, the German Catalysis Society, these are the 5 types of data we need for which we need to get unified formats. So yeah, these are very generic categories, and today we'll focus on a specific one, exactly because of what Brian just said before, of being hard to make tailored solutions for such a variety of data. So today we'll focus on performance data, and here with an addition, I would not like to focus really on performance data, so to say, but I would call kinetic catalytic data. So performance data is related to the performance of a catalyst, but that means that it can be influenced by any transport phenomena. So it might not be really reflective of the catalytic action. So I'll prefer to work or to focus on kinetic catalytic data, which means that it's under the kinetic regime and is purely reflective of the catalyst action. But for all purposes, the same can be applied to performance data, to generic performance data. So now that you have the focus of the type of data that will be the focus of our discussion today, we can move to what is really kinetic catalytic data. So as I was saying, this is the data one gets at an experimental setup by testing a catalyst. I will mainly focus on heterogeneous catalysts, but again, it's also applicable to other types of catalysis. And yeah, you will measure the outlet of your reactor or the product in some way, and that's how we typically measure the performance or the kinetic action of our catalyst. To which kind of data this corresponds to? But we'll have always the independent variables, so the things as variables that you as a researcher can play with, and this is of course the catalyst properties, also the operating data, so temperature, pressures, etc., and the reactor data, which can play with hydrodynamics, the shape of the reactor, and so on. On what you'll measure, this typically the outlet stream or the product stream of the reactor, and this is based on one or a few analytical methods. This we typically convert to flow rates, concentrations, compositions, to better understand what happened in the reactor, and finally, mostly based on the material balance, you'll be able to calculate a few performance indicators. So this is what kinetic catalytic data is, and that's what we'll be working with today. On a side note, I would also like to mention that the way which variables you share, it's also relevant for the usability of your data. So if you share performance indicators, that is what was most common to see in papers, so activities, selectivities, for instance. But this does not allow for the use of the raw data. So for recalculation of performance indicators, for instance. So it's already useful if people share flow rates, but of course the raw data is really the analytics the analytical data. So that's really what is a fair sharing practice for kinetic catalytic data. Now, what are the characteristics of this data? That's what we need to know before starting to reuse it. I will be classifying the kinetic catalytic data in terms of the typical, or at least one of the most used classifications for big data, for the sake of analogy. And these are the 5 V's. So I will start with variety, and variety means in terms of the format that one can find. In catalytic data, you can we know basically, as is exemplified also here, which variables we need to measure. So, and this can already be represented in a tabular manner with common values. So variety is very small in catalytic data, so there's not much to account that for. That's a good thing, clearly. Also, in terms of velocity, that's not a problem. Velocity, for instance, can be a problem when you do a bank transaction, but when you acquire data at the lab, typically you will only process it a few minutes, hours, days after, so there's not a velocity issue in most cases. Then there's veracity, and that's always a question. It also came up in Barry's presentation about the trustworthiness. I would say I believe this is a very positive point because it's more data for cross-checking. Of course, it will be better if we know a priori that data is trustworthy. I think there are some things we can do and we can discuss about that. But the main point is the more data is there, the more you can cross-check other data, and that's the main point of scientific data sharing in my perspective. Now, when it comes to volume, the story is a bit different. Kinetic catalytic data are relatively small, so this data takes quite some time to acquire. I would say a few data points per day in a very optimistic scenario, which means that for a single catalyst, you will only acquire some kilobytes of information. If you are able to group all the data from a given reaction with plenty of catalysts that have been tested in the last few decades, then we are talking a size of about a few megabytes, while true big data is on the size of terabytes for a daily average. So it's a huge gap between what we are doing with catalysis data and the typical big data that most people are referring to. And still, okay, there's some big catalytic data which will come from, for instance, operando characterization and other type of measures that do generate much higher amount of data points than kinetic catalytic data. But for what we are concerned today, we are talking of very small data in the context of big data, but still there are two data sizes that matter and in which one can find differences. So bottom line, we have to take into account this small volume when trying to explore the data. Then the last V, it's value. And in kinetic data, as in most scientific data, this is about information. So information is not directly proportional to the volume of the data, to the number of data points. For instance, you can simply think about experimental design. If you would design an experiment changing temperature and pressure, if you do this in a purely linear way or a pure symmetrical distribution, you might be missing the most informative data points because most effects in catalysis are not linear or are non-linear. While if you have some knowledge of your system, you maybe just target specific points in which you will get most of the information you need. So information is also can be quite variable, and it's a parameter we need to take into account when exploring data in catalysis. So the point, of course, of now that we know what are the characteristics of our data, the next point, of course, is to go from data to information to knowledge, as the work by Medford very well illustrates, and that's what I'll be talking about for the rest of this presentation. Here the details are not so important, but it's again a very nice illustration by Medford. So there's the starting point, which is data, which today we'll restrict ourselves to kinetic data. Then to get to information, you can use a lot of statistical techniques to get to the next step. But to really get into the knowledge about the catalytic system, Medford claims, and I completely agree, that we need to get to a kinetic model or microkinetic model that can fundamentally describe our system. So that's the tools we can use in catalysis to explore the data there is in literature. So we'll take two examples today. I'll talk about two case studies in the next minutes. One is a single kinetic data set, so the smallest, let's say, one can have in kinetic catalytic data, and the second one being a historical reaction data set, so of a larger volume. In the first case, we're talking about small data, and the first step there it's indeed to try to get the maximum information out of this data. Even if these data are small, there will be plenty of small data sets, so there's a need for the automation of this information extraction. So the goal is to go from the raw data that we have been describing to a computer classification of the main trends in the data. That is the information one is looking for in catalysis, is what are the trends, let's say conversion versus pressure, selectivity versus conversion, what are the main catalyst features in terms of the trends in the experimental data. So that was the purpose of our research, and to do so, we built a tool in Python. So this tool takes data, treats the data, and creates sub-data sets that are meaningful in catalysis. By that, I mean, relations between variables that are to be explored. So as I was saying, conversion versus pressure and meaningful relations or meaningful graphs that one could explore. These graphs are then generated by the tool, and then goes to the core of the tool, in which the curves that you can see on the right hand side are generated. So curves that are not overfitting for a very small number of points. So you can see here we are talking between 5 to 10 points, which is quite small. And part of our work was to make sure that the algorithm would not overfit for such a small number of points. The second part of the tool is what is called the primitive recognition. So the recognition of the various shapes in the trends that can then be stored and further used for automated processing of the data. One of that use is then going to knowledge, as I was describing some minutes ago, and there, knowledge being a kinetic model. So for that, we do start with the data and get and recognize the main features in that data, as I just described. And on the other hand, we take a library of rate equations based on the so-called Langmuir-Isherwood-Hugen-Watson kinetics, so typical kinetics for heterogeneous catalysis. This library was constructed, and based on this library, we generate theoretical curves. So to be clear, the input here is only the stoichiometry of the global reaction, and then the rate equation. All possible rate equations are automatically generated, and for these theoretical curves, so which would produce the same type of graphs as in the data, are generated. In the next step, we compare this, so the features in the data and the features that the model can reproduce, and rank rate equations. So in this method, it's possible to screen kinetic models and out in an automated manner. So from data to a kinetic model in a completely automated manner. To give you an example, we took a very old case. In fact, a textbook case that we typically use here at Kent University for ethanol dehydrogenation. So you can see now the experimental curve. This curve was the data in this curve was fed to the tool. The tool was able to recognize two features. So a first increase and then immediately a drop. And this was fed to the second tool, in which there's the library of rate equations. So what you can see here, it's the models that were outputted by the tool that could explain this global reaction. And as you can see, model E or model in figure E is the only one that can explain this type of trend, in which there's first a steep increase and then a decrease in the data. All other models are not capable of doing so. So they were excluded by the tool, and we were able to get to a model in an automated manner. What I would like to refer again here, it's the very small number of points that with which we were able to do so. So here you can see we are only working with 5 data points. So this is very, very small data. We'll move now to the next type of data. So that's historical data, which is of considerably larger. So here I will not count the number of points, but we are talking about dozens of points. And in this case, there's also noticeable difference. We are talking about different catalysts and not different operating conditions as in the previous one. So we have a larger data set, but with but also different in information. So this is for the oxidative coupling of methane. It's one of the few reactions in catalysis for which there's an extensive database. You can look for it and you'll find immediately a few databases that are available, which can be immediately reused without much further processing. So in this perspective, having all different catalysts here, it's still difficult to explain why these catalysts perform differently. So that was our goal in this case for knowledge. It was to understand the relation between the different catalyst parameters that were changed. So you can see here different elements and the composition being changed, and then the performance that you can see in the axis. So how do you take this to get a mechanistic understanding of how the catalysts are operating? We decided to take a microkinetic model, but in this case, as the data is not enough to make one model per catalyst, we just simulated plenty of catalysts via this kinetic model, and we compare them to experimental data via statistics. So we simulate the catalysts based on a fundamental microkinetic model. We compare the performance of this catalyst with the performance of the experimental catalyst, and it's via that matching that then we compare the kinetic properties of the simulated catalyst from the model with the specific properties of the experimental catalysts. So now on the left-hand side, you can see the result of the simulations. So all the open symbols correspond to simulated catalysts. So we were able to cover basically the entire range of performance in terms of selectivity and conversion. And you can see the closed symbols are some of the experimental catalysts. What we did afterwards, it was to apply a clustering technique. So we grouped the catalysts by performance. And you can see here there are 4 groups: the red, the yellow, the green, and the blue one. And you can see that 3 of the experimental catalysts pertain to the yellow group, while other 4 pertain to the green group. So they were clustered in terms in different groups and can now be compared with the corresponding virtual catalyst, so the simulated ones by the model based on those properties. So that's what we did afterwards. So here you can see the comparison. You can see in the y-axis the properties, the kinetic properties in the model. So a reaction enthalpy in the first figure and the chemisorption enthalpy in the second one. And yeah, the basicity that was measured experimentally on these 2 clusters of catalysts. And you can see clearly that the basicity is affecting the properties in the model. So the catalysts in the green group, which are much stronger, they were able to decrease the reaction enthalpy for the proton abstraction, so better activating the reactant, and also they were also able to increase the chemisorption of the chemisorption enthalpy of the oxygen. So by combining fundamental kinetics and experimental data, we're able to do this link between the catalytic descriptors, the catalyst basicity, and then understand the differences in performance in this historical data. So to summarize, I showcased two types of data sets that were different in size, which are typical for catalytic data. Very small, a few points data set, and then we are talking about dozens or hundreds of points for historical data sets, but not only the size was different, but also the information. So in the first case, there were multiple operating conditions for fixed catalysts, while in the latter case, there were fixed operating conditions for multiple catalysts, which might have to change the way we approached it. So in the first case, we did a stepwise approach, first doing trend recognition based on a qualitative trend analysis, and then screening the model, getting to the knowledge in terms of the kinetic model. In the second case, as there were not so much information about the kinetics, we had to start from existing microkinetic model to provide a mechanistic interpretation, and then we compared the experimental data with the data from the simulated data from the model to via clustering to get an understanding about what was behind the experimental difference in performances. I'd like to finish with a few take-home messages. So I hope it became clear that catalytic data is typically much smaller than big data, but it can be very information dense, depending on the way you acquire and which type of parameters were played with. Maximal knowledge extraction for any kind of data can only be obtained if you tailor the methodology you are using or the tool to the data itself. So if you would like to reuse data, my message is first get to know your data in terms of volume and information. Define the goal you want to attain with this data. Be it just information on the trends or a kinetic model or something in between. Then design the methodology that can do that job for this specific data. And finally, when you do so, do share your data and share your code. Of course, as much as you are comfortable with, but try always to share it in a fair way. Thank you so much for your attention.
Thank you very much, Pedro, for a really interesting talk. Does anyone have any questions for Pedro? Again, if you're a speaker, panelist, please do just unmute yourself. If you're an attendee, type it into the chat.
Yes. Hi, Pedro. It's a very good, nice presentation of the topic and a really good example of how to build models using lots small data sets. Do you have any experience on getting data from other larger research which has been shared? Or is that a problem also, that there is not enough data published in this area?
That's indeed a problem. There's not enough data already grouped into data sets. So the example I brought here on the oxidative coupling of methane is only on the one of the few ones. I know in electrocatalysis there are already some data sets that are being shared directly. There are some groups in the US even sharing it directly as soon as they make the experiments via throughput experiments. So it's fully integrated and it's shared basically live. But in heterogeneous catalysis, that's not the case. So we still need to build on scale for that to be the case. I think on top of what we'll all be obliged to do, which is sharing our data in the future by funders and all other things that all other carrots that were discussed before. We also need to do this job for the historical data. So all the data that has been published till now, that would still be useful. I think institutions, funders also, but institutions have a big role there to dig out their data, to make it fair and to share it. It's a huge asset for also academic institutions and can make a huge difference in the community if institutions do digitalize their data and share it in a fair way.
Thanks.
Thank you.
Are there any other questions? I have a question, and it comes from sort of a complete naivety about data and reusing data. Is there any risks or controls you need to put in place in reusing data so you don't lose the original fidelity of the data? So a bit like when you take a movie title and translate it into a foreign language and then translate it back into English, you lose the original title. If you were sort of doing multiple reuses from someone else's reused data set, would there be any risks in that? Or is there anything we should be putting into place to make sure the original data is always the source?
Yes, so in one word, I think there will be no such a problem. But as also Brian was saying, yeah, persistent identifiers is really key, at least to make sure it is traceable. So context should be there on the original data in terms of metadata. It's difficult, again, to make this compulsory because there are details that change from setup to setup, even in the same field. But as long as traceability is there, I think we are covering most of the problems. So that's my approach. That's my suggestion is to for people to do reuse it, but always trace it back to the original source.
Okay, so just good practice then, rather than.
Exactly.
Thank you. If there's more questions coming in, thank you again, Pedro. That was a really interesting talk.